Hey everyone, welcome back. Today we're taking the grid inventory UI we built in the last episode and turning it into something you can actually interact with. Instead of just displaying items, the grid will now react to the mouse, preview where an item can go, show invalid placements, support rotation during drag, and commit real move and swap operations through the inventory X component. This is a big step because after this episode the inventory stops being just a UI mockup and starts behaving like a real gameplay system. The first thing we need is a custom drag and drop operation. In Unreal, when a widget starts a drag, it does not just move the widget itself. It creates a drag-drop operation, and that operation is the object that travels with the mouse during the drag. So we're going to create a new blueprint class with drag-drop operation as the parent and call it DDO_inventory. This object will carry all the data we need. While the item is being dragged, we need the item handle, so when the drop happens, we know which real inventory item we are trying to move. We also store the full item view because the UI needs display data like the item definition, size, and current placement. Then we store the source container handle. That tells us where the drag started, which becomes useful when we validate moves, swaps, or later more complex interactions. We also add current rotation. This is very important for this episode because while the player is dragging an item, we want to let them rotate the preview before committing the final drop. Next, we store a reference to the drag visual widget. That lets the drag operation update the ghost image when the item rotates, instead of recreating the visual every time. We also keep the owning player controller. We'll use it to check whether the player is holding the rotation key during the drag. And finally, we add rotate latched. This prevents the item from rotating every single frame while the key is held down. We only want one rotation per key press, not a rapid flicker between the two rotation states. So this drag operation is basically our temporary drag state. Which item is being dragged, where it came from, what rotation it currently has, and which visual should follow the mouse. Now, we need the visual widget that follows the mouse while we are dragging an item. This is not the real inventory item widget, and it is not changing the inventory data. It is only a temporary ghost preview that makes the drag operation feel clear to the player. We'll create a new widget called WBP Drag Visual. Before entering this widget, set the visual ref variable in the DDO to this newly created widget. The structure is very simple, a size box as the root, and inside it an image for the item icon. The reason we use a size box is that the drag visual needs to match the footprint of the item. A bandage might be 1 cell by 1 cell, but a rifle might be 2 by 4 or 4 by 2 when rotated. So the visual size must be calculated from the item data, not from a fixed widget size. Let's name the size box and the image in ghost box and ghost icon. We also add a cell size variable, set to 64, so this drag visual uses the same scale as the grid. That way, if an item is 2 cells wide, the ghost becomes 2 times the cell size in pixels. Next, we create a function called setVisual. This function receives the item view and the rotation we want to preview. This is the function that configures the drag visual whenever the drag starts, and also whenever the item rotation changes. On the function entry node, we add 2 inputs. The first input is item view. Type inventory item view. This gives the function access to the item definition, which is where the item size and cosmetic reference come from. The second input is rotation. Type inventory item rotation. We pass this in because the visual size depends on the rotation we want to preview. The item might be unrotated, or it might be rotated 90 degrees during the drag. Inside the function, the first thing we do is calculate the effective item size. We use getEffectiveItemSize from the inventory blueprint library. For the definition input, we use itemView.itemDefinition, and for the rotation input, we use the rotation function input. The result is an endpoint, so we store it in a local variable called size. Size.x is how many grid cells wide the visual should be, and size.y is how many grid cells tall it should be. Then we set the width override on Ghostbox. The width is size.x multiplied by cell size. After that, we set the height override on Ghostbox, using size.y multiplied by cell size. This is what makes the ghost preview match the actual footprint of the item in the grid. We are not guessing a pixel size manually. We are deriving it from the item definition and the current rotation state. After the size is set, we need the icon. Just like we did in WBP item, we use async load item cosmetic. The definition again comes from itemView.itemDefinition. We use the async node here on purpose. The drag visual should not block the UI while Unreal resolves a cosmetic asset or a soft texture reference. The widget can exist immediately, and the icon can appear as soon as the cosmetic finishes loading. From the onLoaded pin, we create a custom event called onCosmetic. This event needs one input called cosmetic with type inventory item cosmetic. That input is the asset returned by the async load. Inside onCosmetic, we first check if the cosmetic is valid. If the asset reference is missing or something fails to load, this prevents the widget from trying to read from an invalid object. If the cosmetic is valid, we take cosmetic.icon and assign it to ghost icon using setBrush from soft texture. This gives the drag visual the same item icon used by the normal item widget. So at the end of this section, WBP drag visual is fully data-driven. It receives an item view, receives a rotation, calculates the correct footprint size, loads the cosmetic asynchronously, and displays the icon as a temporary ghost under the cursor. Now we go back to WBP item, because this widget is the thing the player actually clicks and drags. First, we make sure the item widget visibility is set to visible. This matters because the widget needs to receive mouse input. If the widget is not hit testable, Unreal will not call the mouse button event correctly. But we need to be very clear about its responsibility. WBP item starts the drag, but it does not handle the drop. The drop logic will live on WBP grid container, because the grid container knows about the container handle, the grid cells, the placement preview, and the final drop location. The item widget only knows which item it represents, through its cached item view. Now we override onMouse button down. When the player presses the left mouse button on an item, we call detect drag if pressed. The pointer event comes from the mouse event input, and the drag key is left mouse button. This node does not immediately move the item. It tells Unreal, if the player keeps holding the mouse button and moves far enough, start a drag operation. Next, we override onDragDetected. This event is called by Unreal only after the drag actually starts. The first thing we create is the drag visual widget. WBP drag visual, so this is the ghost image that follows the cursor while the item is being dragged. After creating it, we set its visibility to hit test invisible. We want to see the drag visual, but we do not want that visual widget to block mouse events or interfere with the grid underneath. Then we call set visual on the drag visual. We pass in cached view because this item widget already knows which inventory item it represents. For the rotation, we use the current placement rotation from the cached view. So the drag starts with the same rotation the item already has in the grid. Now we create the actual drag and drop operation. The operation class is our custom DDO inventory. This operation is the temporary state object that travels with the drag. So we fill it with everything the grid will need later when the item is dropped. We store the dragged item handle, so the drop code knows which real inventory item to move. We store the full dragged item view, so the preview can read the item definition and item size. We store the source container handle, so we know where the drag started. We also store the current rotation. This value can change while dragging when the player presses the rotation key, and the grid preview will read this value to draw the correct footprint. Then we store the visual reference, so the drag operation can update the ghost widget if the item rotates. We also store the owning player controller, because later the drag operation will use it to check if the rotation key is currently pressed. Finally, we assign the drag visual as the default drag visual of the operation, and we set the pivot to mouse down. This makes the ghost follow the cursor from the point where the player clicked, which feels much more natural for grid inventory dragging. From this point on, the item widget has done its job. It started the drag and packed all the needed data into the operation. The actual placement preview and the final move or swap will be handled by the grid container. Now we are going to create a small blueprint object called BP Inventory UI Actions. In a real project, I would have called it BP Inventory UI Controller. To avoid confusing anyone here, we'll simply name it Actions. This object does not control the pawn, it does not handle camera input, and it does not open or close the inventory. Its job is much more specific. It contains the actions that the inventory UI can perform. The reason we create this object is separation. Our widget should mostly handle presentation and mouse interaction. They should know what the player clicked, where the player dropped an item, and what cell the mouse is over. But the actual inventory operations like move, swap, and later merge or equip should be centralized in one place. So BP Inventory UI Actions becomes the bridge between the UI and the Inventory X component. The UI describes what the player is trying to do, and this object decides which plugin operation should be submitted. Inside this object, we add one variable, inventory component, type inventory component. This is the component that owns the real inventory state and exposes the plugin API we are going to call. Next, we create an initialize function. It takes one input called inComponent on type inventory component, and we simply store that value inside the inventory component variable we created. From this point on, every action function inside this object can use the same inventory component reference. We don't need every widget to know how to call the plugin directly. Now we create the main function for this episode, handle drop on cell. This function represents one specific UI action. The player has dragged an item and released it over a grid cell. The function needs three inputs. The first one is dragged item. Type inventory item handle. This is the real handle of the item we are trying to move. The second input is target container. Type inventory container handle. This tells the plugin which container we are dropping into. The third input is target placement. Type inventory placement info. This contains the target grid position and the rotation that was selected during the drag. Now we can start implementing the function. The first thing we need is the current item data for the item we are dragging. We only have an item handle as input, and the handle is enough to identify the item, but it does not directly give us the item definition, the quantity, the placement, or the runtime state. So we take our inventory component reference and call getItemView. For the item handle input, we pass the dragged item function input. I'm going to store the result in a local variable called draggedView. This keeps the graph easier to read, because we will need this same item view multiple times in the rest of the function. This node is a query. It does not change the inventory, it does not submit an operation, and it does not ask the server to do anything. It simply gives us a read-only snapshot of the item as it exists right now inside the inventory component. From draggedView, the most important field for the next step is the item definition. The item definition is what tells inventory X how big the item is, whether it can rotate, whether it is stackable, and which placement rules apply to it. Before we use this view, we check if it is valid. A valid item view means the handle actually points to an item that exists in this inventory component. If the view is not valid, then the UI should not try to guess what happened. The return value is an inventory operation submit result. This is important. We return the real result from the plugin operation. We are not creating a fake result manually in Blueprint. The operation result is produced by inventory X, and it contains the operation status, result code, operation ID, and affected handles. We will do this later, but in that invalid case, we simply call try_move_item using the same inputs we received, the dragged item, the target container, and the target placement. This might look a little strange because we already know the view is invalid, but the point is that we want the plugin to produce the real operation result. The inventory X operation pipeline will reject the request safely and return the correct result code. This keeps the UI layer thin. We are not inventing failure states inside the widget logic. The plugin remains responsible for validating inventory operations. If the dragged view is valid, we can continue with the real placement preview logic. The next node we call is canPlaceItem at placement. This is one of the most useful query nodes for grid-based inventory UI. It lets us ask the plugin, can this item definition be placed in this container, at this grid position, with this rotation? Again, this is only a query. It does not move the item. It does not update the container. It does not create a pending operation. It only evaluates the placement and returns information that the UI can use. For the container input, we use target container. This is the container that received the drop, so in our current UI, it is the main grid container. For the placement input, we use target placement. This placement was built by the grid widget from the mouse position. It contains the grid top left cell and the rotation currently stored in the drag operation. For the item definition input, we use draggedView.itemDefinition. The placement system needs the definition because the handle alone is not enough to know the item footprint. The definition contains the item shape and the rules that affect placement. Now, one very important option here is bExcludeSelf. We set this to true, and then we pass dragged item as the excluded item. This matters when the player drags an item inside the same container. Imagine the item is currently sitting at cell 00, and we are dragging it slightly to the right. If the layout query did not exclude the item itself, the item would collide with its own current cells, and many valid moves would be reported as blocked. By excluding the dragged item, we tell the layout query, pretend this specific item is temporarily not occupying its current cells. That gives us the correct result for a move preview. The output of this node is an inventory placement result. I'm going to store it in a local variable called layout because it describes the layout result for this attempted placement. The first field we care about is bSuccess. If bSuccess is true, the placement is valid, the cells are available, and the item can be moved there. So we add a branch using layout.bSuccess as the condition. On the true branch, this is the simple case. The item can fit in the target placement, so we call try_move_item. This is the moment where we move from preview logic to command logic. canPlaceItem at placement only asks the question, try_move_item submits a real inventory X operation. For try_move_item, we pass the dragged item handle, the target container handle, and the target placement. Because the placement includes rotation, this one node supports both normal moves and rotated moves into free space. We return the result of try_move_item directly from the function. This is important because the caller, in our case the grid widget, can use was operation successful on the real submit result. Now we handle the false branch of the placement result. If layout.bSuccess is false, it means the item cannot simply be moved into that placement as an empty cell move. But not every failed placement is the same. Sometimes the placement fails because it is out of bounds. Sometimes it fails because a rule denied it. Sometimes it fails because the footprint overlaps one or more existing items. The inventory placement result gives us a colliding items array. This array contains the item handles that are blocking the attempted placement. For this episode, we only treat the placement as a possible swap if there is exactly one colliding item. If there are 0 colliding items, then the failure is probably not a swap case. It might be out of bounds, invalid rotation, or another rule failure. If there is more than one colliding item, we also do not perform a swap, because the dragged item footprint is overlapping multiple items at the same time. That is not a clean one-to-one swap. So we check if length layout.collidingItems is equal to 1. If the length is not 1, we call try_move_item and return its result. Again, this lets the plugin reject the operation with the correct result code. The UI does not need to manually decide every possible failure reason. Again, we will return here on the false branch later. If the length is exactly 1, then we have one item under the attempted placement. This is the interesting branch. The player may be trying to swap with that item, or if the two items are stackable and compatible. They may be trying to merge stacks. We get the first item from the colliding items array at index 0 and store it in a local variable called target item. Now we need more information about this target item. The handle tells us which item it is, but it does not directly tell us its definition or stack data. So we call getItemView again, this time passing target item as the item handle. We store that result in a local variable called targetView. Just like before, we check if targetView.bisValid is true. If the target item view is not valid, something is inconsistent or stale, and the UI should not try to manually fix it. In that case, we fall back to tryMoveItem. The plugin will validate the operation and reject it if it cannot be performed. If the target view is valid, we can decide whether this should become a merge or a swap. The first check is whether the two items have the same item definition. We use equalObject and compare dragView.item definition with targetView.item definition. We compare the item definition object references because this is the actual data asset that defines the item type. If the definitions are different, then these are different item types. A rifle and a bandage should not merge, for example. If the item definitions are different, we go directly to try swap items. That submits a real swap operation to the inventory component. If the item definitions are the same, then the two items might be merge candidates, but we still need to check if this item type is actually stackable. For that, we use the inventory blueprint library function is stackable. We pass in dragView.itemDefinition. This helper checks the stack rule on the item definition. If the item has a stack rule with a max stack size greater than 1, then it can be treated as stackable. If the item definitions match but the item is not stackable, then we do not merge. In that case, we call try_swap_items. If the item is stackable, we call try_merge_stack. We pass the dragged item as the source item and the target item as the stack we want to merge into. This is a real plugin operation as well. The plugin will still validate the merge, including stack compatibility, quantities, and any fragment matching rules defined by the stack rule. We are adding this merge branch now because it naturally belongs in the same drop handling function. But we are not going to focus on the full stacking workflow in this episode. We will demonstrate splitting and merging properly in the next one. So the final decision tree is pretty simple. If the placement is free, move the item. If the placement is blocked by exactly one item, check whether it can merge. If it cannot merge, try to swap. And for any other invalid case, submit the move and let the plugin return the real failure result. The important architectural point is that this function never manually edits the inventory arrays, and it never manually moves the widgets. It only chooses which inventory X operation to submit. After one of these operations succeeds, the inventory component updates its internal state. Then it broadcasts the container change event. Our grid widget is already listening to that event, so it refreshes itself from a new container view. That means the UI is always redrawn from inventory data, not from assumptions made during the drag. This is also why returning the real submit result is useful. The grid widget can call was operation successful on the result and decide whether the UMG drop event should be considered handled. At this point, BP inventory UI actions gives us a clean place for item interaction logic. The item widget starts the drag. The grid widget calculates the target cell, and this actions object chooses the correct plugin operation. This pattern keeps the project easier to extend. Later, when we add split stack, context menus, equipment, hotbar actions, and external containers, we can keep adding inventory actions here instead of spreading that logic across every widget. So let's finish adding the actions we postponed earlier, and then we can consider this part complete, since it was the longest one. Now we need to tell the local player controller to create this object and pass it to both the inventory widget and the grid widget. Then we'll update some of the functions we created in the previous episode. So let's open the player controller. In the not valid branch, where we check if the inventory widget is valid, add a construct object node and set its class to BP inventory UI actions. Then promote the return value of this node to a variable named UI actions. From this new variable, we call the initialization function we created in the object, passing in the inventory component. From this point on, the object will be ready to do its job. To pass the component, we can simply call getComponent by class on the controlled pawn. As shown on screen, before creating the UI actions object, we first check whether it already exists. If it does not exist, we create it. If it does, we skip the creation. Now let's open WBP inventory. Move what we currently have in event construct into a dedicated initialize function. This way we can pass parameters to it, in this case the UI actions object we just created. So let's create a new function called initialize. Add two parameters to this function. The first parameter is component of type inventory component. The second parameter is UI actions of type BP inventory UI actions. Promote these inputs to variables as soon as they enter the function. Now we need to give WBP grid container a reference to the BP inventory UI actions object, because the drop events are handled there. So from event construct, double-click on the setup grid function to open WBP grid container on that function, since we are going to add an input to it. So here we also add an input called in-UI actions of type BP inventory UI actions. Promote this new input to a variable as it comes into the function, so we can use it later in the drop event. Now let's go back to WBP inventory. Now we can copy everything currently inside event construct and paste it into the initialize function we just created. Previously, we were getting the component via a cast on the player, but now we can remove that logic and simply use the new component variable instead. Meanwhile, we pass the new UI actions variable into the setup grid function. As the last step in this section, we need to go back to the player controller and call the new inventory widget initialization function, since it is no longer initialized in event construct. We pass it UI actions and the inventory component. Now we go back to WBP grid cell because we need the cells to show placement feedback during drag and drop. But the important role here is that the cells are still only visual. They do not decide if an item can be placed, they do not handle the drop, and they do not call inventory operations. The actual validation comes from the inventory X component, through the grid container. The cell only receives a visual state and changes its color. First, we create an enum called eCellHighlight. This gives us a clean list of highlight states. The enum has 4 values: none, valid, invalid, and swap. None means the cell is in its normal state. Valid means the item can be placed here. Invalid means the placement is blocked or not allowed. Swap means the item is over exactly one other item, so the UI can show a possible swap. Then, inside WBP grid cell, we add a variable called highlight mode with type eCellHighlight. This variable stores the current visual mode for this cell. Now we create a function called setHighlight. This function takes one input called mode, also type eCellHighlight. Inside the function, we simply store the input value into highlight mode, and then we call another function called applyVisualState. We define it right now so we can drop it in here, and we'll finish implementing it later. We separate these two steps on purpose. setHighlight changes the state, and applyVisualState is the one place that converts that state into actual colors. This keeps the graph easier to maintain later if we want to change the visual style. Now we can implement applyVisualState. The first thing we check is whether highlight mode is different from none. If the highlight mode is not none, then the cell is currently part of a drag preview. In that case, we set the border color based on the highlight enum. For valid, we use a green color. For invalid, we use red. For swap, we use yellow. These colors are not inventory logic. They are just UI feedback for the player. If highlight mode is none, then the drag preview is not affecting this cell anymore. In that case, we restore the normal cell color. Here we use the beOccupied variable. If the cell is occupied, we can make it slightly darker or different from an empty cell. If the cell is empty, we use the normal empty cell color. Even though we introduced beOccupied earlier, we still have not used it anywhere. So for now, nothing will ever happen based on this variable. This matters because during drag and drop, we will constantly apply and clear highlights. When we clear the highlight, the cell needs to return to its correct normal state, not just to one generic color. So the flow is, if the cell has a drag highlight, show the drag color. If it does not have a drag highlight, show the normal occupied or empty color. Again, this widget is still dumb. It does not know why a placement is valid, invalid, or a swap. The grid container will calculate that using the plugin, and then it will tell each cell which visual state to show. This is a good separation. The plugin validates the inventory rules. The grid container decides which cells are affected, and the cell widget only displays the final color. Now we move to the most important widget for this episode, WBP Grid Container. This is where the drag and drop system actually comes together. The item widget starts the drag, and the drag operation carries the temporary drag data, but the grid container is the widget that understands the grid. It knows the cell size, it knows the container handle, it owns the cell widgets, and it has access to the inventory component and our BP inventory UI actions object. That is why all the drag over and drop logic lives here. The individual cells stay visual only, and the item widget stays the drag source only. The container is the only widget that has enough context to convert a mouse position into an inventory placement. The first helper function we need is cell_from_drag. This function takes the pointer event from UMG and converts the mouse position into an inventory grid cell. The input is a pointer event, and the return value is an int point. That int point will represent the grid coordinate under the mouse. X is the column, Y is the row. First, we get the mouse position from the pointer event by calling getScreenSpacePosition. This gives us a screen space coordinate, so the value is a vector 2D in absolute screen coordinates. But our inventory grid is not working in screen space. We need to know where the mouse is relative to the actual grid panel. So we use absolute to local coordinates. For the geometry, we use the cached geometry of cell grid, and for the absolute coordinate, we pass the screen position we just read. The output is still a vector 2D, but now it is in the local coordinate space of the grid. So if the mouse is at the top left of the grid, the local position is close to 0, 0. Now we convert that pixel position into a grid coordinate. We divide localpos.x by cell size, then floor the result to get the column index. Then we divide localpos.y by cell size, and floor that result to get the row index. From this point on, the rest of the drag system can work in inventory cells instead of screen pixels. Next, we create a small cleanup function called clear highlights. During drag and drop, we are going to color cells green, red, or yellow, depending on the placement preview. But every time the mouse moves, the preview can change, so before drawing the new preview, we need to clear the old one. This function loops through the cell widgets array. For each cell widget, we call setHighlight, and we pass none. Because the cell widget already knows how to apply its visual state, the grid container does not need to know the exact colors. It just tells every cell you are no longer highlighted. This is also useful when the drag leaves the grid, or when the drop happens. We can always call this function to reset the drag preview layer. Now we build the function that previews the placement while the player is dragging an item over the grid. This function receives two inputs. The first one is the drag operation, DDO inventory. That gives us the dragged item definition, and the current drag rotation. The second input is cell, an endpoint. This is the cell under the mouse, and we treat it as the top left cell of the attempted placement. The first thing we do is create an inventory placement info. The placement kind is grid. The grid top left is the cell input, and the rotation is DDO.currentRotation. This is important because the preview is not just checking where the mouse is, it is checking where the item would be placed with the current rotation selected during the drag. Next, we call canPlaceItemAtPlacement on the inventory component. This is a query node from the plugin. It does not move the item, and it does not change the inventory. It only tells us whether this placement would be valid. For the container, we use this grid container's container handle. For the placement, we use the placement we just built. For the item definition, we use ddo.draggeditemView.itemDefinition. We also set b exclude self to true, and pass ddo.draggedItemHandle as the excluded item. This matters because while dragging an item inside the same container, the item is still technically occupying its old cells. Excluding it lets the query evaluate the move as if the dragged item was temporarily lifted from the grid. The result is an inventory placement result. If layout.bSuccess is true, the placement is valid, so the highlight mode is valid. If layout.bSuccess is false, we check the colliding items array. If there is exactly one colliding item, we use the swap highlight. If there are 0 collisions or more than one collision, we use invalid. This gives the player immediate feedback: green for a valid move, yellow for a possible item interaction, and red for an invalid placement. After deciding the highlight mode, we call clear highlights. This removes the previous preview before drawing the new one. Now we need to know which cells should receive the highlight. The item might be 1 by 1, 2 by 4, 4 by 2, or any other footprint, so we cannot highlight only the cell under the mouse. We call getEffectiveItemSize using the dragged item definition and DDO.currentRotation. The result is an int point. X is the number of cells wide and Y is the number of cells tall after rotation. Then we use two loops. The outer loop goes through the Y offsets from 0 to size.y minus 1. The inner loop goes through the X offsets from 0 to size.x minus 1. For each offset, we calculate the real cell coordinate to highlight. Cell.x and cell.y are the top left cell under the mouse. Offset x and offset y are the current offset inside the item footprint. So the current highlighted cell is top left plus offset. Cx equals cell.x plus offset x, and cy equals cell.y plus offset y. So we save these results into a variable for convenience. Before using that coordinate, we check if it is inside the grid. X must be greater than or equal to 0. X must be less than cached dimensions.x. Y must be greater than or equal to 0. And Y must be less than cached dimensions.y. This bounds check is important because the player can drag near the edge of the grid. Part of the footprint might be outside the container and we don't want to read an invalid array index. If the cell is inside the grid, we convert the two-dimensional coordinate into an array index. The formula is index equals cy times cached dimensions dot x plus cx. Then we get that cell widget from the cell widgets array and call setHighlight, passing in the mode we calculated earlier. Now that the helper functions are ready, we can connect them to the actual UMG drag events on WBP grid container. The first event is on drag enter. This fires when a drag operation enters the grid container. We cast the operation to DDO inventory. If the cast fails, this is not one of our inventory drags, so we stop. If the cast succeeds, we call preview highlight. For the drag operation input, we pass the cast result. For the cell input, we call cell from drag using the pointer event. This gives us the first preview as soon as the dragged item enters the grid. Next, we override on drag over. This event is even more important because it runs while the drag is moving over the grid. Again, we cast the operation to DDO inventory. If the cast fails, we return false. I copy the cast logic I used earlier because we will need it here and in other places. If the cast succeeds, we call preview highlight again, using the current pointer event to calculate the current cell under the mouse. Then we return true because this grid handled the drag over event. The reason the preview happens in onDragOver, and not only in onDragEnter, is that the mouse can move from cell to cell. Also, the player can rotate the item while the mouse is still over the same cell. So we want the preview to update continuously during the drag. Next we handle onDragLeave. When the dragged item leaves the grid area, we call clear highlights. This prevents the grid from keeping all preview colors after the mouse is no longer over it. Finally, we implement onDrop. This is called when the player releases the mouse button over the grid container. We start by casting the operation to DDO inventory. If it is not our inventory drag operation, we return false. If the cast succeeds, we clear the highlights immediately. At this point, the preview phase is over, so the grid should no longer show drag colors. Then we calculate the drop cell by calling cell from drag with the pointer event. This gives us the grid coordinate where the item was released. Now we build another inventory placement info. The kind is grid, the top left cell is the drop cell, and the rotation comes from DDO.currentRotation. This placement is the final placement request that we want to submit to the inventory system. Before submitting anything, we check that our UI actions reference is valid. If it is not valid, we return false, because this grid does not have the action layer needed to submit inventory operations. If UI actions is valid, we call handle drop on cell. We pass the dragged item handle, this grid container's handle, and the placement we just created. From here, BEP inventory UI actions decides whether the operation should be a move, a merge, or a swap candidate. The grid container does not directly decide all of that. It only knows where the player dropped the item. The function returns an inventory operation submit result. We pass that result into was operation successful, and we use that boolean as the return value for the UMG drop event. If the operation succeeds, inventory X updates the real inventory state. Then the component fires the container change event, and our grid refreshes from the latest container view. If the operation fails, the inventory state does not change, but the drag preview has still been cleared, so the UI does not stay stuck in preview mode. At this point, the grid container owns the full drag and drop interaction, converting mouse coordinates to cells, previewing placement, clearing highlights, and submitting the final drop action. The last piece for this episode is rotation during drag. We already have drag and drop, and we already have placement previews, but now we want the player to be able to press R while dragging an item and rotate its footprint before dropping it. The important thing is that we are not rotating the real inventory item immediately. While the item is being dragged, we only rotate the drag preview. The actual inventory state changes only when the player releases the mouse and the final drop operation is submitted. So we open DDO inventory, because the drag operation is the object that lives during the drag. It already stores the dragged item view, the current rotation, the drag visual reference, the owning player controller, and the rotation latch boolean. We override the dragged event. Unreal calls this event repeatedly while the drag operation is active, so it is a good place to check whether the rotation key is currently being pressed. To keep the event graph clean, I'm putting the rotation logic inside a function called handle rotation, and then I call that function from the dragged event. Inside handle rotation, the first thing we do is check if owning player is valid. We stored the owning player controller when the drag operation was created, and now we use it to read keyboard input. If owning player is not valid, we treat the key as not pressed. That keeps the drag operation safe and prevents us from trying to read input from a missing controller. If owning player is valid, we call his input key down on that player controller, and we check the R key. So at this point, we have a boolean that tells us whether the player has pressed the rotation key. Now we need the latch. The dragged event can run many times per second. If we rotated the item every frame while R is held down, the item could flicker back and forth between the two rotation states almost instantly. That is why we use BRotate latched. It allows one rotation when the key is first pressed, and then it blocks additional rotations until the key is released. So we check two things. The key must be down, and rotate latched must be false. If both are true, this is a new rotation press. We set rotate latch to true, so this press cannot trigger again until the key is released. Then we toggle current rotation. In this tutorial, we only support two states, none and clockwise 90. If the current rotation is none, we switch it to clockwise 90. If it is already clockwise 90, we switch it back to none. After changing current rotation, we update the drag visual. We call setVisual on the stored visual ref, passing the dragged item view and the new current rotation. This is what makes the ghost image resize while dragging. For example, a 2x4 item becomes 4x2 when rotated. Now we handle the release side of the latch. If the rotation key is no longer down, we set rotate latch back to false. That means the next time the player presses R, another rotation will be allowed. The grid preview is already reading DDO.currentRotation inside on dragover. So once current rotation changes, the next dragover update recalculates the placement preview with the new footprint. And finally, when the player drops the item, the grid builds the final target placement using the same current rotation. That means the rotation is committed as part of the move operation. So the flow is. During drag, R changes only the drag operation state and the ghost visual. The preview reads that state for feedback. And the real inventory item is updated only when the drop submits a valid inventory X operation. At this point, the full interaction loop is in place. Drag an item, preview the footprint, rotate during drag, and drop it into a valid cell to commit the move. Now we will spend about 5 minutes debugging, just like in the previous video. These are all simple manual errors, no logic mistakes. The first error is in WBP item. On drag detected, I forgot to connect the return node, so I never passed the drag operation DDO inventory to it. The second error is still in this widget, but on mouse button down. I manually forced the return value to handled, whereas I should simply return the result of detect drag if pressed, which is exactly what this function is meant for. Now the drag and drop works. We only have some visual issues left. Personally, I prefer to grab the ghost widget from its center or possibly from the top left corner, so I'm going to set it up that way. Also, the cells become brighter while a drag is in progress. This happens because we hard-coded the colors in several different places without keeping them consistent. This offset makes it easier for me to see exactly where I'm dragging the object. In WB P grid container, go to the onDrop event. Before the return node, add a branch to check whether the operation succeeded. If the operation was successful, simply return true. If it failed instead, call clear highlights before the return. As a final step, let's set the default cell color so it stays the same in all 3 places where we modify it. Since this is a tutorial about how to use the plugin, I did not spend much time on the visuals, but the look can be whatever you want, and of course it can be far more centralized and polished than what I'm doing here. And that's it for this episode. We now have the core interaction layer for our inventory grid. Items can be dragged. The grid gives us live placement feedback. Invalid positions are highlighted. Items can be rotated while dragging, and the final drop is submitted through real inventory X operations instead of manually moving widgets around. The important part is that the UI is still data-driven. We preview the player's intent in the widgets, but the inventory component remains the source of truth and validates every move. In the next episode, we'll build on top of this system and focus on stacking. We'll add a proper split and merge behavior, create a quantity dialog, and make stackable items like bandages feel much more complete. Thanks for watching, and I'll see you in the next one.